Hello everyone. In this video, I'm going to explain um, the concepts of intersymbol interference and intercarrier interference on DMT systems and OFDM systems. My explanation will be general, so I will not be tied to specific details from DMT systems or OFDM systems, but rather I want to explain the general concept of intersymbol interference and intercarrier interference on multi-carrier systems, okay? But first of all, I think it's worth to take a moment and take a look at the convolution and some of the aspects that I want to show you along the explanation and how I view the convolution and how I like to represent it. So most of the time the convolution y of n between two sequences, let's say x of n and h of n, is most of the time expressed as a summation from minus infinity to positive infinity of x of n and a shifted version of h of n. Okay, but this representation is too complex to the way I want to explain ISI and ICI utilizes a different representation. It's more graphical, and I use tables to show the convolution. So first of all, I want to explain how I'm going to see the convolution. So let's assume, for example, a sequence x of n, which is composed by four samples x0, x1, x2, x3, okay? And another sequence h of n, which is composed by four samples as well, h of 0, h of 1, h of 2, and h of 3, okay? And I want to evaluate the convolution y of n between x of n and h of n, okay? So the way I like to represent convolution is by using a table. In this table, in the first row of the table, I write one of the finite sequences. It's important to emphasize I am dealing with the convolution of discrete finite sequence, okay? So in the first row, I write the first sequence x of n, x1, x0, x1, x2, x3, and then I divide the columns, okay? Here it is, and this is my first row. There's another row here, a third row, a fourth row, and a fifth row. Okay, and next, what I do is I write the second sequences in the first column of the table. So in the first column, I have h of 0, h of 1, h of 2, h3, okay? What I do next is I write the first sequence x of n again on each row. However, when I write it on the second row, for example, I shift it by one index, okay? So let me write here the index n, okay? So this is n equals 0, in the second column n equals 1, n equals 2, and so on and so forth, okay? 5, 6. Okay, so in the second row, I write again the first sequence, but shifted. So I start in the second column, and then x of 0, x1, x2, x3. Okay. The same thing for the third row, x0, x1, x2, x3, okay? And for the fourth row, similarly, x0, x1, x2, x3. My final row is the result of the convolution y of n, okay? So we can see the result of the convolution y of n has 7 samples. And why is that? Well, the first sequence has 4 samples. The second sequence has also 4 samples. And we know the convolution between two finite, the discrete convolution between two finite sequences with length a and b has length a plus b minus 1. So in this case, y of n has length 4 plus 4 minus 1, which is equal to 7. So 7 samples in y of n. And what are the samples in y of n? Well, the way I like to see it is for example, the first sample in y of n, which is y of 0 here. Y of 0 is x of 0 times h of 0. So it's basically the product between the elements in the correspondent column multiplied by the correspondent values or samples from the second sequence, which is in this first column. And so to emphasize it, let's see what's the value for y of 1, which is the second sample of the resulting the result of the convolution y of n. So y of 1 is basically x of 1 times h of 0 plus x of 0 times h of 1. Similarly, y of 2 is x of 1 times h of 0 plus, x of 2, here's the 2, x of 2 times h of 0, x of 1 times h of 1, and x0 times h2. So it's basically the summation between each element in the column above, so x of 2, x of 1, x0. And each of those elements are multiplied by the corresponding sample from the second symbol, which is in the first column, h0. So y of 3 is x3 times h0, x2 times h1, x1 times h2 plus x0 times h3. Okay. So let's do it again, just one more time to make it cleaner. x1, x0, x2, x3, x1, x2, x3. So let's use again the first two samples in y of n. So y of 0, and the table had h0 here, h1 here, h2, and so on and so forth, and so on, and so on. Okay, so here. So y0 is equal to x0, h0. x0, h0. Y of 1 is equal to x1, h0 plus h1, x0. This times this, this and this. So this is it. This is how I see convolution. And we'll see in a moment how this facilitates the understanding of ISI and ICI. Okay, so to start the explanation of ISI and ICI, it's important to recall first the structure of the DMT or OFDM symbol in the time domain. And so let's recall first that in the DMT or OFDM chain there is an IFFT block. IFFT. And to the IFFT block enters as an input the frequency domain DMT symbol, and the output is the time domain DMT or OFDM symbol. And the time domain symbol is a block of data, time domain data, with n samples, provided that this IFFT is an endpoint IFFT. Okay, so after this time domain symbol is generated, it goes to a block called cyclic extender, which appends a cyclic prefix, CP, or a cyclic suffix. So after that, the symbol achieves a structure which is composed by a cyclic prefix, a block of n samples, which is the result of the IFFT, and a cyclic suffix. Okay, so this has n samples, this has new samples, and this let's use tall samples. Okay, all right. What's the composition of the cyclic prefix? How is it formed? Well, the cyclic prefix is the repetition of the last new samples from the data block, from the IFFT. Okay, so basically the cyclic extender block gets these last new samples from the DMT symbol and copies it and appends in the beginning of the symbol. Similarly, the cyclic suffix, is the copy of the first tall samples from the DMT symbol. Okay, so now let's go back to our time domain representation of the DMT symbols by means of its samples, and then show how the cyclic prefix and the cyclic suffix is formed. So suppose again I have a sequence x of n which has 4 samples, x0, x1, x2, x3. This could be the output of an IFFT. So it could be the data which represents the DMT symbol in the time domain. So for a 4-point IFFT, that means n equals 4. For a 4-point FFT, x of n could be the DMT symbol. So let's assume it is the DMT symbol. Okay. So how the cyclic extended DMT symbol would be formed? Let's assume the cyclic prefix has length 2. And let's assume the cyclic suffix has length 2 as well. So the cyclic extended symbol would be x2, x3, the last 2 samples from the DMT time domain symbol, and then the data samples x0, x1, x2, x3, and finally the copy of the first 2 samples from the time domain DMT symbol, which is x0, x1. So this would be the cyclic prefix, this would be the data, and this would be the cyclic suffix. Okay, so this is the copy of the first two samples, and the cyclic prefix is the copy of the last two samples. Now, let's take a look on the reason behind using the cyclic prefix and the cyclic suffix as a copy. Okay, so here's our symbol. Here's the cyclic prefix, the 4 samples of data, and the cyclic suffix. See as data and cyclic prefix. So let's do once again our table and verify the result of the convolution. Okay, so let's assume a channel impulse response with 4 samples as before. So this would be the first row of the table, which corresponds to 8,0, and then the second row corresponds to 8,1, the third row corresponds to 8,2, and the fourth row corresponds to 8,3. Let's divide the table. Okay. And now, let's write the shifted versions of the symbol. So x2, x3, x0, x1, x2, x3, x0, x1. Again, x2, x3, x0, x1, x2, x3, x0, x1. And finally, x2, x3, x0, x1, x2, x3, x0, x1. Okay. So, in the receiver side, what the receiver would do is to interpret the receiving sequence as a string resulting from the convolution, and then the receiver would find where the symbol, the actual DMT symbol, starts, and then slice the symbol. And so let's assume the receiver instantaneously verifies the transmit symbol as in its input. So let's assume the channel has no propagation delay, and at the time that the transmitter is actually transmitting x2, the receiver is already seeing it in its input. So for the receiver Rx here, the index would be 0 here. So let's put the index here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember, in this particular case, we are using n equals 4, nu equals 2, and tau, the length of the cyclic suffix, equals 2. So the symbol has a total length of 8. And the length of the channel impulse response, which is commonly referred as LH, is 4. So the convolution has a length 8 plus 4 minus 1, which is equal to 11. Okay, so it starts at index 0 and ends at index 10. Okay, so let's verify the result of the convolution in the interval that the receiver interprets to be the interval where the data, the DMT symbol data lies. So In this case, in this particular case, that the receiver instantaneously detect the transmit symbol, this is the interval where the receiver interprets the sequence to be the data of the DMT symbol. So note the following. Here, in this column, for example, there is a periodicity x1, x0, and then it wraps around and goes back to the last sample of the data symbol, x2, and then x1. This is exactly how the column of a circular convolution would look like. And similarly, for this column, it starts at x2 and then go x1, goes down to x0, and then wraps around and goes back to x3. The last column from the data part of the received symbol, it starts at x of x3, goes down to x2, goes down to x1, and goes down to x0. So these three columns respect the result that would be observed if the convolution was a circular convolution instead of a linear discrete convolution, the one that we explained in the beginning of the lecture. So we can say that this linear convolution, because the first samples of the transmit symbols are the copy of the last two data samples from the symbol, and because the last two samples from the symbol are also a copy from the first two samples from the data part of the symbol, there is a periodicity in the convolution. And so if we observe these three columns, the result is exactly the same as the result that would be obtained if the convolution was a circular convolution. However, note here the first sample of the receive symbol, the receive time domain symbol. It starts at x0 and then wraps around as it should do. It wraps around to x3 and then goes down to x2, and then for this column to be a result equivalent to a circular convolution, it should present a x1 here. But note, there is no x of 1 here. So this is what we name intercarrier interference. And why is that name? Well, if we take a look at it, the receive symbol, after let's do as follows. So the transmit symbol sends a CP, then data, and then CS. And so there is a stream going out of the transmitter, and the receiver gets a stream. And then at some point, the receiver decides that this point is the beginning of the symbol. And so it counts the amount of samples that corresponds to the CP, and then it knows the number of samples, the number of data samples, and the number of cyclic samples. And then there is another one, and so on and so forth. So the receiver interprets the sequence as a CP, a data, a cyclic suffix, a CP, a data, a cyclic suffix. And then it throws away the CP, throws away the CS, and gets only the data. And the data is exactly what I've shown before. So the data has 4 samples in this case, n equals 4. And there is y as the received sequence corresponding to the data, solely to the data. So there is y0, y1, y2, y3. Okay. So let's see what's y1, y0, y1, y2, y3. Remember, the appearance of the table was as follows: x0, x1, x2, x3. And then wraps around here, goes down, wraps around, down to x0 here, wraps around x2, goes down to x1, x0, wraps around, goes out to x2, x1, x0. Okay, so h0, h1, h2, h3. So y0 is, remember from our explanation, x0, h0 plus x3, h1 plus, sorry for that, plus x2, h2 plus, sorry, that's it. y1 is x1, h0 plus x0, h1 plus h2, x3 plus x2, h3. Okay, so note y1 and the other ones, y2 and y3, all of them have 4 partials in the summation. And this is exactly the result of a circular convolution. But note, y0 has only 3. There is a sample that should be here for the sequence to be equivalent to a circular convolution. But it's not. And so, ideally, I can say that y ideal of 0 would be x0, h0 plus x3, h1 plus x2, h2 plus x1, h3. But this value is not present, and so y ideal of 0 can be stated to be equal to y0 plus an interference, which is y ICI of 0. Okay. So here's the concept of intercarrier interference. Intercarrier interference, or ICI, is the samples is due to the lack of samples in the time domain received sequence corresponding to the data part of the symbol that are not present for the sequence to be equivalent to a circular convolution between the transmit data, time domain data, DMT or OFDM symbol, and the channel impulse response. Okay. And why is it called intercarrier interference? Note the following. In the time domain, there is a sample missing. However, when you take the FFT of this sequence y of n, which is y0, y1, y2, y3, this 3 samples are okay, but this one is not. Not. Okay. So when you take the FFT of y of n, the result is not going to be the product between the FFT of the convolved sequences. Remember, if y of n is equivalent to the circular convolution of x of n, and let's assume this is a symbol for the circular convolution. Okay, so it's a star in between a circle. So if this is true, if y of n is a circular convolution, then the y of k, or the FFT of y of n, is exactly equal to the FFT of x of n, the sequence x, times the FFT of the channel impulse response, which is the frequency response of the channel. Okay. When this is not true, when the convolution is not a circular convolution, the result of the FFT is not merely the element-wise product between x and k. Instead of that, there will be some amplitude leaking away from one subcarrier into another. So let's see as follows. So suppose for n equals 4, the amplitude of, so that this is the magnitude of x of k, and this is k. So let's suppose it's as follows. Okay, and let's assume the channel is as follows. Hypothetically. So the result y of k would be simply the product between the corresponding vectors. So this would multiply this one, and this would multiply this one, and this would multiply this one, and this would multiply this one. However, if the convolution is not a circular convolution, the result would not be simply the element-wise product. And so if we take the FFT of solely the signal that is transmitted on subcarrier 0, for example, let's say subcarrier 1, k equals 1. And so in a k equals 1, the first subcarrier, there is a sequence by definition of the FFT or the DFT. We can think of the FFT or the IFFT as a summation of signals corresponding to different subcarriers. And so if we take the signal from subcarrier 1 and we take the FFT, in the case of the perfect circular convolution, the result y of k, the result in k equals 1 would be simply a vector here, an impulse here, sorry. However, if it's not a circular convolution, the result would rather be an impulse here, but an impulse here, an impulse here, and perhaps an impulse here. That means the signal transmitted on subcarrier 1 is leaking to other subcarriers, and the main requirement for multi-carrier systems, which is that the signals transmitted must be orthogonal to each other, this is broken. So ICI occurs when the linear convolution fails to be equivalent to a circular convolution, and this produces a loss in orthogonality. Okay, so orthogonality is broken due to ICI. So let's now take a look at the ISI effect, the intersymbol interference, and let's do it quicker. So because we already understand the tables, and so we can simplify instead of showing all the details. So let's assume again n equals 4, nu equals 2, tau equals 2. So we have x2, x3, x0, x1, x2, x3, x0, x1. This is the cyclic extended symbol. So here's this p, here's data, and here's cyclic suffix. Okay. So let's do the first column of the table: 0, 81, 82, 83. So what the convolution would do is, let's assume there are in this time two symbols being transmitted. And so let's do once again another symbol here: x2, x3, x0, x1, x2, x3. It continues, but let's stop here. So let's divide here. Here's the beginning of the second symbol: x2, x3, x0. Okay. So what the convolution would do is the linear convolution. Let's put a apostrophe on the second symbol. Okay. Let's mark it. This is the second symbol. So the convolution of the first symbol still leaks in the time domain to the second symbol. So this last sample goes here, then goes here, and then goes here. Okay. And remember, for the receiver, this would be the cyclic prefix, but these 4 samples would be data. And know what happens here. The last sample from the first symbol, which is x1, it's a sample from the cyclic suffix of the first symbol. Due to convolution, it leaks to the cyclic prefix of the second symbol here, and it reaches the data of the second symbol exactly in the point where ICI was present. So at the same time, remember from our previous table that the first sample in y of n would have a missing sample to complete the circular convolution, but it also has a sample that is a sample from the previous symbol in the case of a string of multiple symbols being transmitted. So in this case, there is an x of 1 here, which is from the first symbol. And so if we recall, the ideal y of 0 would be, once again, x0, h0 plus x3, h1 plus x2, h2 plus x1, h3. But the actual the actual receive. Y0 is x0 H0 plus x3 H1 plus x2 H2 plus n x1 from the previous symbol I minus 1 times H3. So this is the ISI in the symbol, and so y of 0 is corresponding to y ideal of 0 plus y ISI of 0, which is exactly x1 from the previous symbol times 3 plus y ICI of 0. And what's ICI? Y ICI of 0? It's the negative of x1 H3. Okay, so it's the ICI is negative because it's a missing sample, a missing value. It's not present, it should be. Okay, so just like the ICI breaks orthogonality, ISI does it as well. Remember, orthogonality comes when the result y of n is a circular convolution between h and x sequences. But since y of 0 is not equivalent to the y ideal of 0, which would be the result of circular convolution, this is not true. This is not true. And so this in the frequency domain, y of k is not h of k, x of k. For the same reason, the signal in a specific subcarrier, let's say subcarrier k, is convolved with the channel impulse response, and then the received sequence, when we take the FFT of the received sequence, it does not appear so as an impulse at subcarrier k, but instead it appears at the other subcarriers. It leaks. So there is a loss in orthogonality. Okay, so to wrap up this video lecture, it is worth to mention the requirements for the system not to present ISI and ICI. So as we've just seen, there is a cyclic prefix, and if this cyclic prefix has a length that is not enough to cover the dispersion of the previous symbol into the present symbol, there is ISI. And since this cyclic prefix in this case is also not enough for the linear convolution to be equivalent to a circular convolution, there is ICI. So, for a system not to present ISI and not to present ICI, the cyclic prefix length should be greater or equal to the length of the channel minus 1. So we can quickly see this as, well, by means of the table again. So if we consider x2, x3, x0, x1, x2, x3, x0, x1, and then if the channel has an impulse response with 4 samples. The last sample in the time domain symbol would go through 4 rows, 3 rows more. So x1 here, x1 here, x1 here. And so if the cyclic prefix is composed by 3 samples, you can see that the last sample from the previous symbol would fall exactly through the cyclic prefix CP of the succeeding symbol, and so there wouldn't be ISI and ICI on the multi-carrier symbols. So the conclusion, nu should be greater or equal than L8 minus 1. And there are lots of more complex details that could be included in this analysis, like synchronization and the cyclic suffix used for alignment, which is commonly the usage of the cyclic suffix, and the technique named as zipper, or the cyclic suffix also used for windowing to improve the spectral shaping of the symbols and reduce interference in other communication systems. Okay, so this is it for now. I hope you learned something about linear convolution, circular convolution, intersymbol interference, and intercarrier interference on OFDM or DMT systems. Hope you enjoyed, and thanks for watching.